Okay, so we introduced discrete random variable last Tuesday. So now we will see how the cumulative distribution function of a discrete random variable looks like. And actually, the CDF of a discrete random variable can be expressed by the probability mass function called PMF of this alright, so is that A less than equal to X for P of A. So you just sum over all PMF value P of A for A less than equal to X. And as you see that because we the P of A is positive only if for countably many possible values A of the discrete random variable. So indeed, this sum is a countable sum. Okay, and so okay, so if we express by possible value A sub I is in a countable index state, as we described on last Tuesday. So that is the expression. Okay, right. So this, so that in here, except for a countable many A P of A is equal to 0. Okay? Oh, many, sorry. And this one is already a countable sum, because the index is from a countable index A. Okay, so that this is the CDF. Okay, and so we will draw. So for example, consider a discrete random variable X with PMF. Okay, so the PMF will be P1 x 1/4, P of 2 x 1/2, and I think P of 1 is 1/4, P of 2 is 1/2, P of 3 is 1/8, and P of 4 is also 1/8. Okay, and the P of A is 0 for all A in R, and A not in 1, 2, 3, 4. Okay. Okay, and so this is 1, 2, 3, 4 x here, and f of x. Now, if x is less than, so if x is less than 1, so you can see for all x less than 1, P of okay, and all a less than x, okay, then f of x, which is P of A, and this is 0, so it's 0. Okay, and so before x equals 1, f of x is all 0 here. And at when x equal to 1, then f1 summation of all a equal to 1 pa, and this is p1, and this is 1/2. Okay, so 1/2. So we have a point here. Now, when x is less greater than 1, and but less than 2, then f of x summation of a less than equal to x, p of a is equal to p1, because that if x is in between 1 and 2 but bigger than 1, so 1 is less than x, less than or equal to x, and so this is p1 and this is 1/2. So we have up to here. Okay, now when x equal to 2, then f of 2 is equal to a less than equal to 2 of pa, and look at the probability math here. So this is actually p1 plus p2, so this is 1/2 plus 1/4. Okay. Oh, I'm sorry. Okay, so that is 1/4. One quarter. This is 3/4. Okay, so here, and 1/4 plus 1/2. So this is 4/4. So this go to here. Okay, this is F2. Okay, and when x is greater than 2 but less than 3, then f of x, a less than equal to x, pa, which is p1 plus p2, and again this is 3/4. So we have a constant up to here. Okay. All right, and here for x equal to 3, f3 a here, and so we have p1 plus p2 plus p3. Okay, so this is the 1/4, 1/2, and 1/8. So that would be 7/8. Okay. So we have. So this is 7/8. Okay, we have this point. All right, and when x is in between 3 and 4, so f of x so this is p1 plus p2 plus p3. Again, this is 7/8. So we have that. Okay. And finally, when x is greater than or equal to 4, f of x a less than equal to x pa, which is p1 plus p2 plus p3 plus p4, which is equal to 1. So that's at 4 is 1, okay, forever. All right, so you can see that so in general, okay, the CDF of a discrete random variable is a stepwise function, okay, with jump. It jumps at possible values AI of size. So what is the size? For here, the size of the jump here is P1, okay, which is 1/4, and the jump here is P2, which is 1/2. The jump here is P3, that is 1/8, and the jump here is P4, which is also 1/8. So the jump at possible values, AJs, and the size, the jump of the size is P of AI. Okay, so that is the general features of the CDF of a discrete random variable. All right, so this is typical. Okay, the CDF should be stepwise. Okay, stepwise, and the jump occur, okay, at possible values of the discrete random variable, and the size of the jump at AI at the possible value is P of AI. It's the probability mass function value. Okay. Any questions? And of course, in addition, sorry, f of x the CDF of a discrete random variable is right continuous. Okay, so it's the right continuous function because that, as you can see, if you approach every function value from the right hand side, you can see the right limit exists and it is equal to the function value. Especially at the jump, you can see here, right? Because this is a solid dot. Okay, so you can see. Right? So when you look at from the right hand side, so they are right continuous. Okay. Right? And we will show that the right continuity is a general property, not only for discrete random variable, but also for any random variable. Okay, discrete or not discrete. Okay. But at least you can observe because it's stabilized and the jump occur at the possible values. Okay, so at the possible value, you will jump up to here and you have a solid dot here. And because of that, you can see that it's right continuous. All right, so we will introduce expected value. Okay, now for a discrete random variable x with possible values I is in a countable index, say capital I. Okay, so you can see that the random variable is equal to a possible value a sub I. Okay, so this event occur with probability p of ai. All right, and so we will sometimes want to know the expectation denoted as E of x of this discrete random variable is defined as the weighted sum of possible values, and the weight, all right, it's just the probability that this random variable is equal to this particular possible value. Okay. Okay. All right. So it's simple to define expectation or expected value of a discrete random variable. If we want to define expectation of a general random variable, that will take some effort, right? But for discrete random variables, so that would be straightforward, just like this one. Okay, so in terms of PMF, we just have P of AI. All right, and because that if the index say is countable by the infinite. I mean, for example, if we have countable infinite many possible values like A1, A2, A3, A4, etc. All right, this sum becomes to a serious sum. Okay, and when it is a serious sum, then you have to investigate whether the sum converge or not. Okay, so we say that the expectation, if we define that, provided that the sum exists. Okay? The sum exists. There are two senses for existence. Okay? And so there are two ways to say that. Either the sum, the series sum, if the sum is a finite sum, of course, there's no problem for that. But if I is countably, if I is a countably infinite, say, index, say. Okay, so if I is a countably infinite index set, okay, the sum exists means, all right. Maybe I write that 1. The series sum if all AI is greater than or equal to 0. Okay, no, I will write down the series sum converge to a finite number, right? So we say exist. The second, very special. If AI is greater than or equal to 0 for all I in index, right? And the series sum diverges to infinity. Okay. Right. So sometimes we still regard. So if all the possible values are non-negative, then of course this sum should be non-negative. But it is possible the series sum diverge to infinity. Okay, unbounded. It is possible. Okay. So existence means not only for the first sense, but also the second sense here. Okay. But when you say that the sum is finite, if the sum is finite, then that means the first sense, the series sum must converge to a finite limit, a finite number. Okay, and so you have to use a lot of criteria you learned from calculus, right? Because in calculus you learn several techniques to justify whether a series sum converges to a finite number, right? Okay, so in this course, that when I say that the sum exists, there are two senses. Okay, so if the value, all the possible values are non-negative, then the sum always exists. Why? Either diverge to infinity or converge to a positive non-negative number, right? There must be so. So, but if a possible value can be positive, negative, or the zero value, okay, then be careful. existence means that the series sum converges to a finite number. Okay. Any questions? All right, let's take an example. 4.3.b. Okay, so we let E be an event of interest in our sigma algebra F, and we define IE omega, right, to be either 1 or 0 if the outcome is in E, if the outcome is not in E. Okay, so by this definition, we know E it's a function from the sample space to the set of all real numbers. And the range is only the set of 1 and 0. Okay, so there are only two possible values. Okay, there are only two possible values. But it's just a function, right? So we have to show that this function is a random variable. Okay, now we look at A. So the event, this event says that so all outcome such that equal to X. Okay. If and you can see that if X is not equal to 0 or 1, it's an empty set, right? Empty set. If X is equal to 0, so if X is equal to 0, okay, by this definition, outcome has value 0 if and only if so if only if this is the complement, okay? Not E, right? But if X is equal to 1, this is E. Okay? So for every real number X, the atomic event, okay, the atomic event here defined by discrete by this discrete function is here. So no matter which one, you can see this is in the sigma algebra. Okay, so all this atomic event described by this function, okay, is in F. So that EI is a discrete random variable, okay? Because we say a random variable, a discrete random variable, is not just a function only with countable many possible value. That every subset like this one should be an event of interest. Okay, and so we just prove that this is indeed the case. Okay, so this is the discrete random variable. Okay, and IE is called the indicator of the event E. The event E. So that we say that if omega, if outcome is in event E, we know that the event. So if we observe outcome omega in the event E, we say that the event E occurs. And then this indicator gives us 1. But if event not occur, then the indicator gives us 0. So indicator is just like a flag, right? A flag stand up. We get 1, we say the event occur because the outcome is in the outcome of the random experiment we perform is in the event E. Okay? But if the outcome is not in the event E, we say the event E does not occur. And so the indicator has value 0. Okay? So we call I is the indicator of event E. Okay. All right, and now the atomic event. Okay, so the atomic event described by the indicator of the event E are what? E, which is just, and E complement. So there are only 2 atomic events associated with the indicator of event E. And you can see that E complement is a partition of the sample space. X, okay? It's a partition of the sample space. From the information point of view, an event E is equivalent to its indicator. Okay. So this random variable, okay, give us the information we can get from the indicator. It's just the event E itself. Because if we know the event E, we know the complement of E. Okay? So they contain the same information. Sometimes it's better to use indicator of an event instead of the event E itself, okay, as you will see later. Okay. Any questions? Okay, now we move on. Consider function of discrete random variables. Okay, we know a random variable, especially a discrete random variable, okay, is the measurement of certain characteristic of an outcome. So that for each outcome, there is a measurement result. Okay, so this X will measure certain characteristics or certain features of the outcome. And in many situations, we will process this feature. All right? So we are going through a function G. G is a function from the set of real numbers to the set of real numbers. Okay, so this is going to do the sum. So this is the data processing function. Okay. All right, so this is going to measurement. And this is data processing. For example, we may take the absolute value of this feature, or we may take the square of this feature, right? So there are a lot of data processing function. Okay. And the data processing function can be any real valued functions. Okay? Okay? And so now by composition of two functions, because as we know, a random variable is a special types of function from the sample space to the set of real numbers. Okay, it is special because that every atomic any atomic event should be an event of interest, right? So that is the basic requirement. All right, and so if we have a composition, okay, and we define this to be, so y is a function from S to R, okay? All right, so now, so the question is y a discrete random variable if x is, okay? So our question is that x is a discrete random variable, and after a data processing function, we get another function y. So our question is y is a discrete random variable? Okay. Now, all right, so first of all, y is discrete since it takes on one of countable possible values g of ai for I in, because the index set capital I is countable, and so the possible value a sub I of this measurement x after data processing, this value, they are all possible values for the function y. And it's countable, of course, because the index is here. So y is discrete. No problem. Okay? But the other is, it is a random variable. Okay? So, all right, so let bj, j in j, be possible values of y. Okay? Where j is countable as described in above. Okay, so we know if we index all possible value of y, then the index set J should be countable. All right? Now, so we look at this event. So this is the smallest possible event can be described by the function y. Okay? All right? So this is the possible. All right? And so this is equal to bj. Okay? And that is g of x ebj. Okay? So that this is and of x omega equal to ai, and with gai equal to bj. gai equal to bj. Okay. Is that okay? It is possible that you have two AIs mapped to the same BJ, right? Under the data processing function G. So for a function, it's possible to be 1-to-1, right? Or many to 1. Okay? So there are many AIs go to the same BJ. It's possible. Okay? Okay, and so what is that? So this is the union of I so the union of possible AI such that G of AI equal to Bj, and okay, so you can write it in this way. And so that y equal to bj is the union of ai such that g of ai equal to bj and x equal to ai. And this is a countable union. Why? Because we have only at the most countable many AIs here. Okay. Okay. So and this one is in because x is a random variable, so that this basic event described by x must be event of interest in the sigma algebra. So each x equal to ai is a member in the sigma algebra F, and we have a count of many of them to take union. So of course this is also in F by the logical structure of sigma algebra. Okay, so we proved that. And so y is a discrete random variable, of course. Right? So we show that for any functions of discrete random variable must be discrete random variables. Right? And because it's discrete random variable, so we can the PMF we call PYBJ of y. It's so now we can compute the PMF of y, which is just P of y equal to Bj by definition, right? And so this is the probability of, by here, the union, and we know this is disjoint union, okay? And the AI such that G of AI equal to Bj and X equal to AI. Okay? And this is disjoint becomes by countable additivity AI G of AI equal to Bj, probability of X equal to AI. Okay, so this is countable additivity of P. Okay. And so finally is AI such that G of AI equal to Bj and the P of X AI. Okay, so this one is the PMF of X. Okay. So the PMF of Y can be expressed by the PMF of X. Okay. Any questions? By the way, the sum, this sum is a countable sum because AI, there are countable many AIs. But this sum must converge, okay, to a final number y. Because the total probability is 1 only. Okay. So that this sum must converge and converge to a number which is in between 0 and 1. Any questions? Yes. The question here? X equal to AI? Because this is a description, this event is equal to this is subset. Yeah, this is another way, because the definition of this event is here. Yeah. Okay, so, yeah. Other questions? Okay. So now there is a proposition. So that X a discrete random variable taking one of the values AI, I is in countable index AI, and the G, a real valued function on R. Okay. Then Y defined to be the composition, right? It's a discrete or subset of R containing all possible OAI. I think that would be good enough. Okay. So because for composition, the domain of the data processing function should be the domain should contain all possible values of x. Okay. Now, so this composition is a discrete random variable. We have shown here, right? We have shown here, and the expectation, we can compute the expectation to be equal to G of AI. So the Y is a function of x, right? So G of x, and it's so the expectation of Y, okay, becomes to the weighted sum of the function values G of AI, and the weighting is by using the PMF of x. The first part has been proved in above. Okay, so we already proved that. All right, so we just do the second part. All right, so let's see the expectation Y. Oh, by the way, we have to say provided the sum exists. Okay, we have to write down these premises. Okay, so so by definition, Bj. All right, because we just show Y is discrete, a discrete random variable, and by definition of the expectation of a discrete random variable, you see, it's just that Bj is possible value of the Y, and this is the PMF of Y. Okay. But we have just shown the PMF of Y, okay, can be expressed by the PMF of X. So that would be an AI such that G of AI equal to Bj, of P X AI. Okay. Now you move Bj to the right. So you have double sum. Okay, and you have Bj. All right, and you have Px AI here. Okay. Now, so in here, the summation, the double summation AI such that G of AI equal to Bj. So now Bj is actually G of AI and P of X AI. Okay, and finally, I in the index and G of AI, P of X, and you have done. Because the double sum will contain all possible AIs. Because the first sum, because you know, each AI will corresponding to some Bj. Okay, because Bj is all possible values of Y. And so if you combine together, this double sum will run over all possible AI. Okay, and so this is the final result. We get here. And provided that the sum exists, of course. So we need to justify whether the sum exists or not. Okay. All right, so data processing of discrete random variable is an easy theme to study because for any such function G, this composition Y is also a discrete random variable, and so we can have the expectation, and the expectation of this processed value, the Y, can be expressed again by the data processing function as well as the PMF of the original random variable X. So, okay, so that means that we can compute the expectation of Y directly by using this formula. Okay. All right. So okay, so I think I will take a break, okay, up to 2:30. Okay, so a corollary of the previous proposition that if the data processing function is a linear function, okay, so consider the data processing function g of x equal to ax plus b. Okay, so g of x is the data processing function. Okay, and so that g of ax plus b, which is the expectation of g of x, right? So this is a summation I in I of g of ai and p of x ai. Okay. All right, and this is and ai plus b. Sorry, p of x ai. Okay. So summation. So it's so we have two terms, so we can plus b ai, right? And so this is expectation of ex. Okay, so, and this is b, because this one is equal to 1. Okay. Things on S of I are all possible values, so, and so this is summation is equal to 1. Okay. So this is a simple application of the proposition 4.1.1. Another useful data processing functions are power functions. Okay, so consider g of x is equal to x to the nth power. Okay, g to the nth power. And so the quantity expectation of xn, which is expectation of g of x, is called the nth moment of x, if it exists. Okay, and by proposition 4.4.1, we have the nth moment to be AI nth power and P of x of AI. Okay. So a special case is about we'll define variance. Okay. So if x is a discrete random variables such that its first two moments are finite, then the variance of x denoted as VAR of x is defined as the expectation of x minus expectation of x square. Okay. Okay. So you can see that the variance is a measure of the dispersion of our possible values. The expectation of x gives us the center of all possible values, weighted by the probability mass of each possible values, right? That is the definition. So you can think about that. It's just like the center, the mass center, the probability mass center of the random variable. That is the so the difference is that possible values from the center. So that is the dispersion, right? So if the difference is big, then that means that the possible value were distributed far away from the center. So that's why this is big. And because the difference can be positive, negative, right? Because before or after. So we take the square, because if we take square, everything becomes positive. So that is the effect of squaring, okay? And then we take the expectation, the average. So that is a measure. So this which is a measure of dispersion of the possible values of x from the center from the center possible values. We call E of x, okay? So it's a measure of the dispersion. Okay, and as we will see that with this definition, okay, so So note that the variance of x by the definition okay, so that is x squared minus 2e plus square okay, and we can repeat it, apply corollary the linear function. So this is actually okay. So this is a constant. This is also a constant. Okay. All right. Constant. Constant. In corollary, okay, so we will go through the same. Okay, and so this is EX squared, but this is a square, so this is minus EX squared. So to compute the variance of x, you need the second moment of x and the first moment of x. The first moment is just the expectation of x. Okay. Okay. So we have this formula here. Any questions? That is a useful identity. For any constants a and b, the variance of ax plus b is equal to the a square of the variance of x. Okay, so the proof as an exercise. Okay. Okay, so I ask you to verify this identity. Okay, and the square root of the variance VAR X is called the standard deviation of X, denoted as standard deviation of a discrete random variable is defined to be the square root of a variance of X. So that is I think the reason to take the square root is here because we have squared the distance. Okay? So that if we take the square, then the dimension will go back to distance. Okay? Okay. So the meaning of the standard deviation is the same. It will describe a measure of the dispersion of the possible value of X from the center possible value E of X. Okay. So that we will see the dispersion. So if all possible value were concentrated together, then the dispersion will be very small, and so the standard deviation will be small. Okay, will be small. But if the possible value were distributed in the right range, okay, and then so that so the variance over the standard deviation will be big. Okay. The next section described two kinds of random variable called Bernoulli and binomial random variables. Okay. So they are discrete random variables with particular probability mass function. Okay, so they can be served as models of practical random variables. Okay, so a Bernoulli random variable X with parameter P is a discrete random variable. So discrete random variable will be abbreviated as D dot R dot V dot. Taking value taking on one of two values 0 and 1 such that the probability that x equals 0 is equal to 1 minus p, and the probability that x equal to 1 x equal to p. Okay. So a Bernoulli random variable is a two-valued random variable, and the two possible values are 0 and 1. Okay. And the parameter p is just the probability that the random variable, the Bernoulli random variable x is equal to 1. Okay. And so because there are only two possible values, so the probability that x equals 0 will be 1 minus p. Okay, so that is simple. Now, we say two discrete random variables. Okay, so two discrete random variables called x and y are called independent. Okay, so if we consider two discrete random variable, for example, x is Bernoulli random variable and y is another Bernoulli random variable, possible, right? But anyway, it's just arbitrary two discrete random variable, and we call them to be independent if for any possible values ai, bj of x, y, respectively. This basic event, x equal to ai and y equal to bj, right? So this is a basic event described by x. This is a basic event described by y. These two events are independent events. Okay? Right. So the meaning to say that two discrete random variables x and y are independent if we take a basic event described by x and a basic event described by y, then these two events must be statistically independent. And this is always true for arbitrary possible value of ai and possible value of bj for y. Okay, so this is true. If we have n discrete random variables called x1, x2, up to xn, are called independent if for any possible values ai1, ai2, ain of x1, x2, xn, respectively, then x1 equal to ai1. So this is a basic event described by x1. x2 equal to ai2 up to xn equal to ain. All right, so now we have n events. And these n events are statistically independent. Events. Okay. Remember, we define that n events are independent, right? If so, we define the condition, and you have to apply that definition here. Okay, so now consider an independent Bernoulli. Now suppose we have n independent Bernoulli random variables. Go x1, x2 up to xn. So x1, x2 up to xn, each of them is a Bernoulli random variable. And they are independent. Right? And we let y to be the sum. Okay? So we let y to be the sum. Now we have to see, because this involves n different random variables. They are different random variables. Even though each is of type of Bernoulli random variable, means that each random variable takes one of two values, 0 and 1. And the parameter with the same parameter, so I have to say with the same parameter p. Okay, so each x of I has this p, so they have the same PMF. Okay. So of course y, okay, and the range of y would be 0, 1, 2, up to n. Okay, so of course this function is discrete because that there are only n plus 1 possible values. Okay, there are n plus 1 possible values. Okay, but the question is, y a discrete random variables? Okay, y is discrete, of course, because that the range is countable. But we have to show that every basic event is an event of interest in the sigma algebra F. All right, so we have to check y equals 0. Y equals 0 if and only if x1 is 0, x2 is 0, xn is 0. Okay? So this is the intersection xi equal to 0. And of course this is in F, right? It's in F. Because each x of I is a random variable, a discrete random variable. So such a basic event is an event of interest. Okay, in the sigma algebra. So the intersection, because we have countable intersections. So this is in F, of course. Okay, so that this one is measurable, and so the probability. So we can compute the probability of this basic event, and by counting with this intersection, and because they are independent, so the probability of and so this becomes to the product. So this is 1 minus p to the n square. Okay. How about y equal to 1? Y equal to 1 is that one of the x of I is equal to 1, and the rest x of I are all has 0 values. So that this is x1 equal to 1. Okay. So maybe we were right here. x1 equal to 1, but x2 is 0. Xn is 0. Disjoint union, x1 is 0, but x2 is 1. But they are all zeros. Disjoint unions, x1 is 0, x2 is 0, 0, but xn equal to 1. Okay. And you can see that this is the intersection and the union. So again, this is in F. Okay. Okay. Intersection of the event in F, right? So this is just like here, we have intersections. Okay, and so this is event of interest. Okay, and if we take a countable union of event of interest, so it's again an event of interest in F. Okay, so it's in F too. And the probability of y equal to 1, so you can see that the probability here, this is p times 1 minus p and minus 1's power. Because in here, we have independence, so the probability of intersections becomes the product of probability of individual event. Okay, so this is here. And again, here we have p, 1 minus p and minus 1's power again. Okay, and how many of them? We have n of them. Okay, n of them. Okay, and in general, if y is equal to y, okay, so that you know this is say x1 equal to 1, xi equal to 1, xi plus 1 equal to 0, xn equal to 0, union, say x1 equal to 0, x1, so that equal to 1, okay, okay, so I of this random variable takes value 1, and the rest of the random variable takes value 0. Okay, so that they are, and so you have so how many terms do we have? So what is how many possible union we have? Okay, so they are n select I. Okay, possible terms in the union. Okay, and so this is in F, of course, because that each event described in this one basic event, the intersection of basic event described by x sub i's. Okay, so they are okay. All right, so no, yeah, not yet probability, just the event itself. So this event y equal to I is an event of interest in F. Okay, and Okay. And so the probability of y equals to I becomes to n sec I and p sub I, p to the i's power and m minus p to the n minus i's power. Okay. Because that 1p corresponding to some xi equal to 1. Okay. And 1 minus p corresponding to some xi equal to 0. Okay. So you will have that. And in general, so this is of course this is in F. Oh, so yn is in F, and probability of y p to the power, and this is n, select n, pn 0. Okay. And this is equal to okay. And this can be written as n1 okay. All right, so from the previous discussion, that's y is a discrete random variable. Because every basic event is an event of interest, okay, by our demonstration here. So that so it's a discrete random variables, okay, and which has the PMF that the Py0 Py I equal to n Pi for I equal to 0, 1, 2, and okay. Okay. So y is a discrete random variable. So the sum of n independent but only random variables, y, is again a discrete random variable with a very special type of PMF. Okay, so any discrete random variable having the above PMF is called a binomial random variable. Okay? And it's very you can comprehend the reason why we call it binomial, because we are using the binomial coefficient to say that. Especially, note that by the binomial theorem, we have 1 is equal to p plus 1 minus p nth power, and this is the summation of I from 1 to n and pi. Okay, so you can see this is indeed a PMF because their sum equal to 1 by the binomial theorem. Okay. In sections 4.7 and 4.8, okay, of the textbook, yeah. Oh, yes, thank you. Thank you so much. Yep. All right, so in section 4.7 and 4.8 of the textbook, there are several special type of discrete random variable. Investigated, such as the Poisson random variables and geometric random variables and negative binomial random variables, hyper geometric random variables, and zeta or Zipf random variables. Okay, so that there are quite a few important special types of discrete random variables, such as Poisson random variables, geometric random variables, negative binomial random variables, hypergeometric random variables, and the zeta random variables. Each type has some special types of probability mass function. Okay, so they are classified according to different types of probability mass functions. Just like for Bernoulli random variables, the PMF is easy, so that this is all right. So if we have PMF like this one, then the random variable x is called Bernoulli random variable with parameter p. Okay, and we also derive a special type of random variable called binomial random variables. Okay, when the PMF is like this one, okay, possible values from 0 to n, and the mass for value I is equal to this quantity. Okay, all right, and so there are quite a few different types of discrete random variables. Okay. All right. So I don't have enough time to describe each of them. So I ask you to read the textbook. Okay. And among them, there are some special properties of them. Okay. So I encourage you to read through the examples, because examples give you the idea and the concept how each types of random variable can be used. Okay, so all right, so that I have to skip of them. Okay, so I think I don't have enough time for that. So so next Thursday we will have the first midterm examinations, and as I announced in the EE class, that the coverage will be from chapter 2 to chapter 4. Okay, and so well, I think I have to stop here, and next Tuesday I will discuss a little bit of the rest of chapter 4. Okay, but I think most of the parts has been discussed already. Okay, so I stop here and see you next week.